Um, Hello, those watching this online. It's semester 2, 2024, and this is a revision seminar for Statistical Modelling and Inference, also known as SMI. This is the first revision seminar ever for this course. So, hello, you're watching history. Okay, so I've been asked some things, and I'm going to talk about some things. Some things to know about this seminar. I'm just going to repeat them. You are allowed to interrupt me. If I make a mistake, interrupt me immediately. Do not wait till I finish a sentence. Just tell me straight away if you notice that I've done a weird minus sign error or any other error. Otherwise, wait to the end of the sentence, but feel free to interrupt to ask questions. If you people notice something appearing in the chat that I haven't noticed, could you let me know? Yes, feel free to ask questions. I will do my best to remember to stop at least every 10 minutes or so to just give you a chance to say things. As I said, first revision seminar, so I may be asking for some of your help to check up what the lecturer has actually said about things. If I do pause the video, I'm trusting you guys to help me remember to start it again so that we don't just have this sudden no more video. Okay. But before I go any further, the vibe of this course is more or less like the probability theory behind the statistical methods that you might have learned in an introductory statistics course. So you learn about making confidence intervals and making hypothesis tests and doing regression in the various mathematical ways that do those things. And so it really heavily relies on you just happening to remember things about matrices and vectors and integrals and probability distributions and that sort of thing. That's something that some people find difficult in this course because your memory is not perfect of those things. Yeah, if you were allowed to write a formula sheet of your own, you would put some of those things on that are troubling to remember. So we're going to hope that your lecturer puts whatever of those things you need. But some of them, the more times you use them, the better chance you have of remembering them. Okay. So pivotal quantities, we're in about week, I don't know, 6 or 7, and so on. And I remember this semester people asking me about them at the time. There was quite a bit of confusion, and in the trimester course, which is at about that spot in the trimester, they're also asking. So it must be something about it that is difficult to process. My understanding of a pivotal quantity is that, let me step back. Things only need names if you have to talk about them. And so a pivotal quantity must have been given a name because you need to talk about it. And you must have needed to talk about it for some reason. And it seems to me that the reason you have pivotal quantities is so that you can make test statistics and so that you can make confidence intervals. That's what they are for, as far as I can tell from the information that has been given in this course. And if you think about your experience of the statistical methods that you may have learned in an introductory statistics course, you'll calculate test statistics. So just some past experience. your test statistics tended to be like Zs or maybe Ts. And you have like a T with an n-1 for like your T test. Or maybe it'll be like an F in a nova, which will have like a G-1 and n-G or something like that. And the idea is that you take your data and you produce this test statistic, and you imagine all of the test statistics that could have happened. And when you do that, the distribution of all the test statistics that could have happened happens to be a distribution that people know about. Because you could imagine doing any number of different calculations from your data in order to help you make the decision about a null hypothesis. Like you could imagine all sorts of different possible things you could calculate, and most of them, they would have distributions, you just wouldn't know what they are. And so the point of a test statistic is having a distribution that you know what it is. And so pivotal quantities are kind of like test statistics. You know what their distribution is. And I'm just going to be even more precise about this. When you do the Z test for a mean, and you have your Z statistic is like X bar minus mu from the null hypothesis divided by sigma on root n, that thing. And then you say, if the null hypothesis is true, then Z has a distribution of a standard normal. That's a classic. This was the first hypothesis test to ever be invented in about, I don't know, 1890 or something like that. And the interesting thing about this calculation is that this bit comes from the data, and this bit comes from the null hypothesis. This is an assumption about, this here is an assumption about what the parameter is that you are trying to ask questions about. And so when we calculated this test statistic, we made a calculation using both the data and the parameter that we're interested in. That is what a pivotal quantity is. It's something that you calculate from your data and from your parameter that has a distribution that you know what it is. And importantly, it has to be like a standard distribution that doesn't require you anymore that you could just look up the distribution of. That's the idea. So I'm pretty sure, I can't be absolutely sure, but my theory is that the name pivotal quantity came up when people were trying to look at the test statistics and things like that that had already been made and try and create some statistical theory to explain how they work. And so they went, all right, I'm going to call this a pivotal quantity. All right. But pivotal quantity is a bit more general. It doesn't necessarily equal a test statistic. But basically, a pivotal quantity can do the job of a test statistic. If you have a null hypothesis that assumes the value of the parameter you're interested in, then you can create from a pivotal quantity a test statistic. And also, you can create from your pivotal quantity a confidence interval. That's the idea as far as I can tell. Yep. The null hypothesis, so this would be like H naught mu is a particular value called mu naught. And so this parameter mu naught is the value of what mu is, which is an assumption. And the X bar comes from the data. You calculate it from the data you have. So this comes from the data. This is an assumption about your parameter, and together they make the pivotal quantity. Okay. So I'm going to do an example that I did in the Maths Learning Centre yesterday, or the day before. Time has no meaning this week. So, well, maybe I'll do this one actually first. So, suppose xi is a normal distribution with mean mu, and does your lecturer put sigma squared in this spot or sigma when they write a normal distribution? Sigma squared. From a normal distribution with mu and sigma squared, and they're independent and identically distributed. Show that z, which is equal to x bar minus mu over sigma on root n for I equals 1 to n, is a pivotal quantity for mu. Pretty sure that pivotal quantities have to be for something. They're pivotal quantities for the parameter. Is that right? Sounds like a grammar thing that would normally be said. Okay. Well, you have to work your way through to how Z was constructed and be sure that it is a distribution that doesn't involve mu, that you know what the distribution is. Okay, so x bar, because of the theory, will be a normal distribution with mean mu and variance sigma squared on n. I'm pretty sure you're allowed to just say that in this course. Unless you're explicitly asked to prove this fact, I don't think you have to prove it. Okay. And when you subtract numbers from a normal distribution, it affects the mean, but not the variance. So if I subtract mu from every value of x bar that could possibly be, the mean will get that number subtracted, but the variance will stay the same. And in my head, the picture is that, like, in my head, in the previous thing, this is what x is with mean mu and variance and standard deviation sigma. And x bar has mean mu and a narrower sigma. Sigma on root n. And then you shift the whole thing down to 0 by subtracting mu from everything. That's the picture in my head. And then you divide by sigma on root n. And when you divide by a number, it divides both the mean and the standard deviation. So 0 divided by sigma on root n is still 0. And the standard deviation is sigma on root n. And so when you divide that by sigma on root n, you get a 1. Since sigma on root n divided by sigma on root n is 1. Standardizing. Yes, that's usually what people call it. So we have standardized the sample mean to create this. And so therefore, Z must be a standard normal distribution. And therefore, which does not involve the number mu anywhere in the in this description of what the distribution is. So no mu needed to tell the distribution, and so therefore Z is a pivotal quantity. Yay! All right, so that one, my argument used facts about how normal distributions work. So this was a fact about how means, the distribution of the sample mean is related to the distribution of the original variables. And this is a fact about linear transformations of normal distributions, and so is this. So both of these, this one comes from add or subtract a constant affects mean but not standard deviation. That's what that one is. And this one is multiply or divide a constant affects both mean and standard deviation. So both of those things are previously known facts about how normal distributions work. In fact, these two things are true of any distribution. It's just that for a normal distribution, the new distribution is also normal. But if you had a binomial distribution and you did those things, you would get a distribution and you would know what its mean and standard deviation were, but it wouldn't be a binomial distribution anymore. It would be something else. So that's just worth noting. So that is showing that Z in the standard, in the Z test for a mean is a pivotal quantity. And what that means is if you make an assumption about what mu is, then you can turn Z into a test statistic that will test whether mu is in fact equal to that number. And it will also allow you to create a confidence interval for the value of mu. So I'm just going to actually do that. I just want to be absolutely certain that we know how to do this. But before I move on, thoughts or questions about this? Okay. Yep. It's the normal distribution is the only one, I think, that the mean and standard deviation tells you which distribution it is. But for the binomial distribution, you have to say the number of trials and the probability of success. And they do have a mean and a standard deviation, but that's not enough to tell you which binomial distribution you have. Because lots of binomial distributions have the same mean and standard deviation, but they're not the same binomial distribution. Does that answer the question? Yeah. Yep. Mm-hmm. Ah, yes. That's because this is the variance, and this is the standard deviation, which is the square root of that. And when you divide by something, it affects the standard deviation. And so this top line here is the standard deviation, and this is the constant that I divided by. So that's the standard deviation. So that's the variance. And so when you square root that, you get the standard deviation. And it's the standard deviation that gets divided by the constant. Yeah. Okay, same situation. Use the pivotal to construct a, I don't know, 95 is the most common, isn't it? Let's do it. 95% confidence interval for mu. So important, remember that a hypothesis test is designed to answer a yes or no question. And in this course, pretty much all of them are yes or no questions about a single parameter. Whereas a confidence interval is designed to say, based on the data, which values for the parameter am I happy to believe? So they're the opposite question. A hypothesis test says, do I believe this value for the parameter? And the confidence interval is essentially doing several hypothesis tests all at once and saying, these are all the numbers that I would retain in a hypothesis test. And so, This requires us to have a really good definition of what a confidence interval is. You may please correct me, but I am almost certain that the definition of a confidence interval is an interval. It might be one-ended or just a second. If they don't tell you what kind of confidence interval it is, it always means it's two-ended. Do they? I can't remember the correct terminology for one that only has one end. What's it called? Sorry, is it one-tailed or? Okay, yeah, okay. All right, but if they don't say it, they mean a two-sided confidence interval, or two-tailed confidence interval, or yeah, okay. And there's a word symmetric, I think, that goes with confidence intervals as well, I think. And if they don't tell you what kind to make, you make a symmetric one as well. Okay, so the idea is that I'm going to make a two-sided symmetric one. So I would like, so when I make a confidence interval, I'll get two numbers. So just as an aside, a confidence interval looks like there's a number here and a number here, right? That's what a confidence interval looks like. And all the numbers in between are the ones that we're happy to believe based on the data we've got. And the ones outside, we would reject those based on the hypothesis test. And they normally traditionally call this L and U. And the really important thing to know about a confidence interval is that you calculate these two numbers from the data. And since they come from the data, that means they are officially statistics, like in the official technical terminology of what a statistic is. A statistic is something that is calculated from the data. So they are each a statistic. And even more so, the data itself is technically a collection of independent random variables, which means that L, the lower end of your confidence interval, is also a random variable because it was calculated from random variables. We don't, as far as I can tell, you don't ever actually find the distribution of L. But what I want to point out is that if you collected different data, you would get different numbers for these things. And so you can make probability statements about the numbers L and U because they're not always the same. And so they have probabilities to go with them. In their probability statements. You can't make a probability statement about the number mu. It's not a random variable. It's just a number. It's whatever number it is. I just don't know what it is. Yeah. So I'm just making that to myself. So just philosophically, it's a thing. And so a confidence interval is something that looks like this, about which I can make a probability statement. And that probability statement will be, the probability will be the level of confidence that I'm interested in. And so what I would like to say is that the probability that the interval LU contains the parameter, in our case, the parameter is called mu, is 95%. That's the statement I want to make. I want to be certain that this pair of random variables, that pair of random variables makes an interval that contains mu. That is an event that happens, and it sometimes happens and it sometimes doesn't. And I would like the probability of that event happening being 0.95. That's what a confidence interval is. Yeah. And so you can imagine there's lots of different choices for what LNU could be to make that true, and you generally try to make it true that, well, I'll draw a picture of it in a second. So I'm going to pull out this statement and work on that and turn this into a probability statement that I can actually know about. Because here's the problem. These random variables, the only way to figure out a probability is to know the distribution. And I don't know what the distribution of L and U are. So I have to turn this statement about some random variables that I don't know the distribution of into a statement about a random variable that I do know the distribution of. And that's what a pivotal quantity is for. So L, I want, so this statement, LU contains mu, is the same as this statement. Aha. And so mu is involved here. And so what I need is a random variable that mu is involved in that I know the distribution of. And I do have a random variable that mu is involved in that I know the distribution of. It's this. And so I'm going to create that from what I've got here. So, no, I'll do one with a sigma later. You mean sigma? Oh, no, I'm not. Yes, I understand what you're saying with sigma, but I just want to finish this. It is technically possible to put sort of sigma there as well. But it wouldn't be a Z we'd be using. We'd be using a chi squared, probably. But yes, so you're saying, is it technically possible to have sigma as the parameter that's in this spot? And yes, it is possible. And so I would have to create this out of the mu that I've got. So I'm going to have to make it be a minus mu, which will cause me to put my variables the other way around. I'm going to have to add x bar to everything. It's not a mu, it's a u. And I'm going to have to divide everything by sigma on root n. Sweet. And now this is Z. I'm going to do two things at once here. I am not comfortable with my inequality being the wrong way around and having the big one at the left-hand side and the small one at the right-hand side. So I'm just going to switch them around. And this is Z. And that is great, because now what I want is the probability of this being 0.95. And Z has a distribution that I know. So here we go. Here's a nice big picture of it. That's Z. This is our standard normal distribution, like that. And I need the probability of being between these two numbers to be 0.95. And this number here is x minus, that's not a mu, David, it's a u. Sigma on root n. And this number here is x bar minus L on sigma on root n. But that's great. So technically I can move both of these, and there's lots of different confidence intervals I could make. The symmetry that they're talking about is trying to make sure that it's the same probability on the outside in each of these spots. So if this is 0.95, together this is 0.05, and so this bit here, this area, must be 0.025, and this area must be 0.025. This is normally called alpha on 2. So this number here is 1 minus alpha usually, which means that the two outside together are alpha, and this number here is alpha on 2. And the name for the number in the Z distribution that has alpha on 2 above it is Z subscript alpha on 2. And so this number must be Z subscript 0.025. And this number, since it's symmetrical, must be Z, minus Z 0.025. It is also Z 0.975. Which is puzzling, actually, because normally when you talk about probability distributions and you talk about probabilities, you're almost always talking about the left-hand side. But when you do these things, which are called critical values, the little number at the bottom is the probability on the right-hand side. And the reason for that is that we only do them when we're doing confidence intervals and hypothesis tests. And so yeah. And so now that I have that, I can undo all of this working I did. And it does seem like double handling because you keep doing things and then undoing them, but I can't see any other way of being absolutely certain of what your answer is. So, and so now we have that x bar minus u on sigma on root n is minus z 0.025, and x bar minus l on sigma on root n is z 0.025. And so I should be able to unwrap my working that I've done before. I can multiply by sigma on root n. Oh, that did not turn out well. And then add mu, and so I get that. That's not what I want at all. I want the u, don't I? That's okay. I'll pop this over there. That was bad move, David. That's what u is, the x bar plus that. And the same working would show that L is x bar minus this. Which is the confidence interval for a mean that you know and love. Yay. Therefore, your 95% confidence interval is has endpoints x bar plus or minus z 0.025 sigma on root n. How are you feeling about that process? It's the only way I know how to do it. Is it similar to what your lecturer did? So I have another example. So this is my example, which just a second. So I found kind of extended something that I saw in the Maths Learning Center, and it started out with yi are uniform distributions with bottom end 0 and top end theta, and they're independent. And what that looks like, I'll deal with that in a second. Where that computer's loud. Okay. What that looks like, no, I can do that. Sorry, bear with me. Yi is this. And I'm going to call, so we've got y1 up to yn, like that. I equals 1 to n. And what I'm going to say is that the maximum of all of these numbers is called y brackets n. That's the usual notation for the last one. When you put them in order, the last one in the list is y brackets n. Y brackets 1 would be the minimum, and y brackets 2 would be the second smallest value. And so this is one of these numbers. I just don't know which one it is. Yeah, so that's what that's going to be. And what we're going to do is we're going to construct a pivotal quantity for theta using yn. And use it to find a 95% confidence interval for theta. That's the thing we're going to do. I know what that, because I did the problem the other day. I know what that pivotal quantity is, but I'm really hoping it's going to appear when I try and do the calculation. So the only way to make a pivotal quantity using this statistic is to know what the distribution of that statistic is. So just to have a picture of yi, there's 0 and there's theta, and this is the PDF of yi. It comes along and it's 0 all the way to here, and then it's the correct height here, and then it's 0 all the way to here. The only a uniform distribution, everything has the same PDF, has the same height along the PDF, and the total area is 1. And so since the area is 1, you know, actually, since it's theta wide, it must be 1 over theta high, because theta times 1 over theta is 1. Like that. It's just, that's what a uniform distribution looks like. Okay. So we need to figure out what the distribution of y brackets n is, what the maximum is. And if you've done the right sorts of things in probability and statistics, then you will be able to do such a thing, theoretically. So let's see. So there are multiple ways to figure out a distribution. And if we're going to make a confidence interval, we actually eventually are going to need the PDF of our distribution, because we're going to have to figure out probabilities. And you can't figure out probabilities from a moment generating function, for example. And usually I would expect a PDF to come from a CDF usually. But also I have a theory. The thing I know about this number is it's greater than or equal to all of these numbers. And so since the definition of this number here already has a greater than or equal to in it, CDFs sound like a good idea, because that's also about less greater than or equal to's and less than or equal to's. So I'm going to do that distribution. So let's see, I want the probability that yn is less than or equal to a specific number, which I shall call y. Okay, this is the CDF of yn. Like this would be capital F yn of y is the probability of yn being less than or equal to y. Cool. Well, I know it's the maximum, right? yi is less than or equal to yn for all I, since it's the maximum. And since yn is less than or equal to y, all of the yi's have to be less than or equal to y as well. And even more, if all of them were less than or equal to, if they were all less than a lower number, the maximum wouldn't have been y. It would have been something else. So if yi was less than or equal to some lower number, then yn would have been less than or equal to a lower number as well. And so therefore, the statement that yn is less than or equal to y is the same as the statement that all of the yi's are less than or equal to y. So when I come back to here, f of yn y, which was the probability that yn is less than or equal to y, is the same as the probability that y1 is less than or equal to y, all the way up to yn being less than or equal to y. The only way that the maximum can be less than or equal to y is for all of the other ones to be less than or equal to y. They're the exact same statement. And since they're independent, I can do this. Like that. And since they're all the same distribution, I'll get that, because these are all the same number, because they're all the same probability. Cool. That's nice. All right. So if my y is between 0 and theta, then the probability of being less than or equal to the specific number y will be y out of theta. Okay. Like that. So we want to know what area this is, and we know the height is 1 over theta. And so the area of this is y wide and 1 over theta high, which is y over theta. Or you can think of it as, well, it's uniform. It's the length of y compared to the length of theta, which is what this is. That will only be true if y is between 0 and theta. If y is out here, the probability is 1. The capital F is 1. And if y is over here, capital F is 0. Because if you've already gone past the end, the total probability is 1. So this is for 0 theta. Cool. That is not a uniform distribution because of the n. But that's okay. We'll be able to cope with that. Okay. Sure. Guess. It's a CDF. I'm going to need to make a CDF that doesn't include, that somehow doesn't have theta in it. Have I done something wrong here? Bear with me, I'm just thinking. The thing that's worrying me is that theta is deeply embedded inside that theta to the power of n there. Just thinking. Yep. This thing here, up here. So that, yes, so you could write them as intersections. Yeah. So commas can be intersections. You can write it either way. That's okay. So yes, I could have written it like that. That's what you're. Yeah. It's okay. We'll cope. We'll see what happens. Okay. That's okay. We'll sort that out. That theta, I want a calc, so I have a CDF for y. I really do want a CDF of, I want so sorry, this y brackets n has this CDF, which does in fact deeply involve theta. I need something that doesn't involve theta. I guess the theta is something that controls how wide this is. And so that would control standard deviation. I've got an idea. What if I changed this? So I know what yn is. What if I change this to have a theta inside here as part of this variable? Because then that might cancel out the theta that's here. Yes, that'll do it. So no one would ever think of this, I think, but I'm going to give it a go. I'm going to let x be equal to yn divided by theta, so that this thing here becomes an x instead of a y on theta. That's what I'm going to do. Because then that wouldn't have a theta in it anymore. It would just be an x. So I'm going to let x be yn divided by theta, and then f of x of the particular number x would be the probability that x is less than or equal to x, which is the probability that yn on theta is less than or equal to x, which is the probability that yn is less than or equal to theta times x. And I know what that is. This is the f of yn, that's what this is, but with the theta x in the spot where the y used to be. And so that must be theta x in the spot where the y used to be from our previous calculation. That's cool. So I saw that when I had this here, it eventually became this. And so when I have this here, it will eventually become the exact same thing, but with the y replaced by theta x. That's a neat little trick, isn't it? Cool. So I reckon if you're ever asked to make a pivotal quantity and you find that it has your y divided by something or y times something, you can let that entire thing be like just x or something, and that will be, or z or whatever, and that can be your pivotal quantity. That's fun. And so this is just x to the power of n. And so the CDF of this random variable does not involve theta. And so it's a pivotal quantity. So CDF of x has no theta, so therefore it is a pivotal quantity for theta. Okay, cool. I choose not to figure out what the distribution actually is. I'm sure there is one, but that's the CDF. If I wanted the PDF, I'd differentiate that. So I guess just for the purposes, the PDF will be nx to the n minus 1 for x between 0 and 1. No, x. Oh, wait. This was for y being between 0 and theta. So this is for theta x being between 0 and theta. And so that means that x is between 0 and 1. So I replace the y in this with x theta. So I have to replace the y in this with x times theta. And so I'm going to do that here. But then if I divide by theta, I get this. It's got to be careful because not just the formula, but also the bounds have to not involve theta. That's important too. How are we feeling about making that pivotal quantity? So you get to decide what method describes your random variable. In the previous pivotal quantity, the description was n brackets something something, and that didn't involve the mu. And in this one, the description is the CDF, and that didn't involve the theta. It's possible to do a moment generating function and not involve the parameter. There's lots of different ways to describe a distribution. And if you can make your whatever description you've got not involve the parameter, then you know it's a pivotal quantity. So our description was a CDF and it doesn't involve theta, so it's a pivotal quantity. Before, the description was a name for the distribution and it didn't involve mu, so it was a pivotal quantity. But you could also have the moment generating function not involving the parameter, and that would be a pivotal quantity. Yes. Okay. You should probably, every time you calculate a CDF, just tell the reader that that's what you're doing by putting the CDF there. Okay. All right. And then I have to make a confidence interval for theta. That was the ultimate goal, wasn't it? Let me just check what. Whenever I do these revision seminars and I do a question, I always say, I'll check what they said. It's like, but it would be me because I made up the problem. So I'll check what I said. Yep, had to use it to find 95% confidence interval. Okay, so I need a 95% confidence interval is an interval LU so that the probability of LU, oh crap, it's supposed to be round brackets, I think. Or is it square brackets in your course? No one cares, they're continuous variables anyway. Contains, and this time it has to contain theta because that's the number that we're trying to estimate. All right, and we need that to be 0.95. And so this statement that LU contains theta is the same as the statement that L is between, that theta is between L and U. Maybe not equals. Before I said or equal to when I did it, so it must be square brackets. Sorry about that. If you use round brackets, make them strictly less thans, and if you use square brackets, use or equal tos. But I don't think the people reading it will care. I don't know for sure. Have a look in your notes and see whether they use square or round in the videos and that sort of thing. So we know that statement is the same as this statement. And we want to use our pivotal quantity to figure out what L and U have to be. And our pivotal quantity was y brackets n on theta. So I need to arrange to have a y brackets n on theta. And so my first step will be to have 1 on theta. Now, this move when you do 1 over, it reverses the inequalities. Because if this is a small number and that's a big number, then when you do 1 over, this will become a big number and this will become a small number. And technically, this move is only possible if all of these numbers are positive, which they are, because you know theta is between 0 and you know that theta is more than 0. And so your lower bound for theta is definitely 0 at the very lowest. So that's okay. Okay, since all positive. Okay, that's all right. And now I need to arrange my pivotal quantity to appear. So I'm going to multiply everything by y brackets n. And that there is what x is. And I will just switch my inequalities over. That's not a theta, that's a u. Sorry about that. I did two things at once there. I reversed the order of everything, which had reversed the inequality signs, and I replaced that with x. Cool. And so it should be possible now to figure out what these things are. I want the probability of x being between these things to be 0.95. So my PDF for x was n times x to the power of n minus 1. So that looks something like this. That's my PDF for x. And so I would, oh no, let's just spread that out a bit. That's my PDF for x. And I would like to choose a spot in the middle that is 95%. That's what I want here. And I need this number to be yn on u, and this number to be yn on L. But I actually don't know what the name of this distribution is for x. So the only way for me to figure out what these numbers are is to just figure them out rather than just go, oh, it's like a d sub 0.25. So I'm going to need this to be 0.025 and this to be 0.025. And so I need the integral of, actually, I need the CDF at this spot to be 0.025. So I need the CDF fx of yn on u to be 0.025. That's what I need. But that's okay. I know what the CDF is. It's x to the power of n, wasn't it? Yep, that's what it was, x to the power of n. So this thing, power of n, has to be 0.025. And so therefore, yn on u has to be the nth root of 0.025. And so u therefore has to be yn on the nth root of 0.025. That's what u is. Cool. Oh, I use PDF to draw the picture, but I need the area to be 0.025, and the CDF is what talks about the area. So the PDF talks about the height, which allows me to draw the picture, but the CDF tells me the area, which allows me to calculate the area. So I need the area, and so therefore I need the CDF. And also I need fx of yn on L to be 0.95 plus 0.025, because that's the total area so far. So that's the total area that is before that point. And so that's going to eventually come out to same deal. Really could have, like, I could have predicted that. But that's okay. So yn on 0.975 to the 1 on n is what L is. Oops, sorry, knocked my camera. And so the 95% confidence interval is yn on 0.975 to the 1 on n, and yn on 0.025 to the 1 on n. Yay! I'll put all of that on one camera. Yeah, it's not that good. All right. So previously, we didn't use the actual CDF to do the calculation. We just said, oh, it's Z sub alpha on 2, because you can just look that up or get R to calculate that number for you. But with this one, I didn't actually know what the name of this distribution was, and so I just calculated it using the actual integral. I have no idea if this is the sort of thing your lecturer would ask you to do, but it's all stuff that theoretically you've seen before. I've just put it together in this new way. Yeah. And that's the idea of pivotal quantities. You had before you said, can we do something with a variance? Yep. Yes. So if you wanted to do a confidence interval for a variance, then you would do something else. So one last example. That same deal. Dependent I equals 1 to n. If you wanted to make a confidence interval or a hypothesis test for a variance, then you would need to know a pivotal quantity for the variance. So this is where some of the probability theory that came in, where there were some, workshop or assignment questions or videos or something saying how the sample variance is related to the to what the distribution of the sample variance is. And so if you have the sample variance, that's the sample variance. You need it to be an unbiased estimator, which is why the n-1 is there and not the n. And I mean, you don't need it to be, but whatever. And it turns out that if you divide this by sigma squared and multiply it, like, I think multiply by n-1. Someone might have to help me look this up. I'm pretty sure that this quantity, I shall call it x, is from a chi-squared distribution with n-1 degrees of freedom. Almost certain. If you look at that, the n-1 makes this go away. So this thing here, and we're dividing by sigma squared ends up being a chi-squared distribution with n-1 degrees of freedom, which is fascinating because normally a chi-squared distribution with n-1 degrees of freedom would be the sum of n-1 standard normal distributions. But it looks to me like we've added standard normal distributions squared. So you get n-1 independent standard normal distributions and you square them and you add them up, then that produces a chi-squared distribution. And it looks like we're adding n, normal distribution squared. But it turns out that we're actually only adding n-1 because of the y bar being made out of the yi's. There's a proof somewhere that does that. And so this is a pivotal quantity because the description of this distribution does not involve sigma. It's not this that is important. It's this that's important. There is no sigma anywhere here. The only thing that we need to know in order to know what this distribution is n and not sigma. No sigma in this description. And also, very helpfully, nowhere in any of these calculations have we used the value of mu either. So you really don't want your pivotal quantity to use one of the other parameters if you've got two of them. Because if you do, then you need to know what that parameter is. So interestingly, look at this one. This pivotal quantity, here, which was a pivotal quantity for mu, it's technically also a pivotal quantity for sigma, because it does in fact create a distribution that does not involve sigma either. But the problem is, the only way to calculate this is to know at least what mu and sigma are. So if you want a hypothesis test or a confidence interval about sigma that doesn't require you to know what mu is, then you can't use this one. But theoretically, if you knew in advance what the mean of your normal distribution was, and all you wanted to know was what the variance was, you could use this as a pivotal quantity for sigma if you wanted, which is kind of cool. That's actually really cool. I've never thought of that before. But this one is better for sigma because it does not require you to know what mu is to calculate it. And that's why the t statistic is better for mu than the z statistic, because the t statistic doesn't require you to know what sigma is in order to calculate it. And that's why it's better. Whereas if you do know what sigma is, this is easier to do than the t, and easier to do the maths for, because the t distribution is like sucks. Like it's like a standard normal divided by chi-squared. Like, I don't know. It's just not a fan, honestly. It's probably done with moment generating functions or something. Okay. So that is how you would make a confidence interval or a hypothesis test for a variance without knowing what mu is. So I'm just going to put some of that down. There's no mu here either. So so it's good for when you don't know what mu is. And this is not a pivotal quantity for mu because you can't use it to figure out what mu is. So I mean, it's technically a pivotal quantity for mu because its variance, its description doesn't involve mu, but I'm pretty sure that we can't use it to make we just can't use it to make a confidence interval for mu because it doesn't mention mu. That's a problem. So if I wanted to do a hypothesis test on this or a confidence interval, I could do a confidence interval. 95% confidence interval for sigma squared. So that means I need L and U so that the probability that LU contains sigma squared is 0.95. And so I would work on that and see where I go. I'm going to need a 1 over like I did before. Okay, since positive, it's squared. And I'm going to need to multiply by n minus 1 and s squared. To create my pivotal quantity. And then this thing is x. Oh no. I'm just going to switch this round as well because I don't like having them the wrong way around. And since x is from a chi-squared distribution with n minus 1 degrees of freedom, what's that? Oh, yep, I forgot to flip one of them. Thank you. That's not very, let's do that. Since it's from a chi-squared distribution, we need the middle bit here to be 95%. So we need 0.025 here and 0.025 here. And this number is s squared n minus 1 over u. And this number is s squared n minus 1 over L. Okay. And the chi-square distribution is not symmetrical. And so I can't just make this one the critical value for chi-squared and this one minus that, because for a start, that's a 0 just there. The chi-square distribution starts at 0. And so I definitely can't do that. So I'm just going to have to do them separately. And so I do know that this one is going to be the chi-square distribution with n minus 1 degrees of freedom critical value for 0.025 because it has 0.025 above it. And this one will be the chi-square distribution with n minus 1 degrees of freedom critical value 0.975 because it has 975 above it. Of course, if I wanted to calculate what this number was, this number in R would be Q chi-square 0.025 n minus 1. Because when you use the Q function in R, you have to tell it what the probability is below. But when you use this notation, you have to tell it the probability above. I wish it were not so, but that's the way it is. And so we've got that s squared n minus 1 on u is chi-squared n minus 1, 0.975. And so therefore u is s squared n minus 1 over the critical value for my chi-squared distribution. And similarly, s squared n minus 1 on L is chi-squared n minus 1, 0.025, which means that L is s squared n minus 1 over that critical value, 0.025. And that's my confidence interval. Yay. So something that's happened in all three of these is that the lower end of the confidence interval ended up coming from the upper end of the distribution. And the upper end of the confidence interval came from the lower end of the distribution. It's happened 3 times. It must be I'm saying that's quite common. Expect it. But I have a feeling that some pivotal quantities will not do that. And sometimes the lower end of the confidence interval will come from the lower end of the distribution. So just keep an eye out for it. Yay. Well, that was I feel better. Now, next year, when someone comes to me in the Maths Learning Centre and says, what's the deal with pivotal quantities? I can say, I did a revision seminar on it last year. Let's give that a go. Where are the rest of my words? I've gone straight from 8 to 11. That's great, David. All right, that'll do. For that. Would you like me to talk about regression? Distribution of what? I like the prediction. Okay. I'll see where I go. But before I do that, I did want to ask if I am going to talk about multiple regression, what specifically do you want me to talk about for multiple regression? The what? Contrasts. Oh, okay. Just going to pause for a second while I think about that. All right. So I'll say a couple of things about my thoughts, and then we'll get to the contrast thing. So just want to orient myself to what's going on, and hopefully it helps you as well. Multiple regression is the third kind of question that statistics is trying to answer. And so we already had that there's three questions that statistics can answer, and they are yes or no questions, usually about a parameter or other parameters. And that's what hypothesis testing is for. You know, rejection regions and p-values and stuff. And there is a what's this number, which is also concerning parameters. Which is what confidence intervals are for. And there is a what's the relationship? Or if you like, what's the formula? No, I will say relationship. Which is what regression is for. But the thing is that in order to ask a question about what's the relationship, you sometimes have to ask yes or no questions. Because the question of what is the relationship between these variables, inside that question is the kind of more important first question of, are these variables related? Which is a yes or no question, and therefore has a hypothesis test to go with it. And then if you've made a relationship that's got some numbers in them, you're going to need to know what those numbers are in order to have a formula. And so you're going to have to make confidence intervals as well. And so just pointing out that this tends to contain those other questions. But since these two, we made our statistical methods answer these questions by wondering about parameters. We're going to answer these questions by wondering about parameters as well. So that's that. But before I get there, there's like an outcome variable, which is traditionally called y. And you're wondering about what some other things are that may possibly allow you to predict the value of y. This is a picture in my head of what regression is for. And it may be that these variables each like independently affect y, but it may also be that these variables affect the way that the other variables affect y, which is what an interaction is. So it may be that somehow these two things that x2 may affect the way that x1 affects y, for example, and that's an interaction. So that's multiple regression. That's what it's for. And it doesn't really matter whether these things are categorical variables or numerical variables. It'll all be fine. But linear regression is definitely designed for this to be a number. That's a number measured on a scale. Though there are regressions where this isn't, like logistic regression, but I wouldn't expect you to have seen that in this course. Does that? No? Okay. Okay. So the thing is that being a maths thing that we're doing, we want to pitch our question about the relationship as maths. And so we write a formula, something like this. This would be the formula approximately that goes with this situation here. I've got a starting value. I've got a value times the value of x1. I've got a number times the value of x2. I've got a number times the value of x3. And not beta 1 times beta 2, a new number, which I'm calling beta 1, 2. A new number, which is multiplied by both x1 and x2, and that will allow me to figure out whether x2 affects the way that x1 affects the result. And so this is called an interaction term, this thing here. And these are terms because that's a maths word from polynomials. The full model is that each individual value of y that you collect is based on the individual values of x that belong to that thing, plus a little bit of error. So what we're imagining is that the way the universe decides what the value of y is today is to look at all the values of x that you currently have, all the x values of the various different x's, put them into this formula and calculate a value of we're kind of go starting value for yi, and then we're going to add a little bit, which might be positive or negative, and that's what's causing the randomness. So the interesting thing about the way that we think about regression is that none of this bit is random. Only this bit is random. Yeah. So this bit here, that's where the randomness comes in. And so the yi will be random, but only because the epsilon I is random. Yeah. And the big assumption you make is the epsilon I has mean 0, and all that does is require you make your plane or line of best fit actually be in the middle of the points instead of offset by a bit. And that it's a normally distributed, and and that no matter what values of x you've got, it's always the same variance. So if you have all the same values of x for an individual, then individuals that all have the same value for all the x's, they'll all have different y's because of the epsilons. And when you look at those values, that variance for those y's that go with that combination of x's, they should have the same variance with that combination of x's as they do for another one. That's the idea. But that's where the randomness comes from. Yeah. So it is important to be able to think about it in this way, even though there's going to be some matrix things going on as well. It's still important to be able to think of it this way and put it back in this format. And so each of these are the coefficients. Each of these coefficients is a parameter which can allow you to ask yes or no questions by asking yourself whether those parameters are equal to specific numbers or not. So the most basic and fundamental question you can ask about any of these parameters is whether they're 0 or not. Because if the parameter beta 2 is 0, then No, so if the parameter beta 3 is 0, then x3 doesn't actually appear in this formula at all. And so, in fact, x3 isn't related to y. And so the question here of is x3 related to y is the same question as asking, is beta 3 equal to 0? And a yes or no question about the value of a parameter, that's a hypothesis test. So do h naught beta 3 equals 0. That's the idea. And so, and the question of, so there's multiple ways to ask the question. You could say, does x2 affect the way that x1 affects y? Is also asking the question of, does the relationship with y depend on the combination of x1 and x2 or just separately? Yeah. All of these questions are the same question of, do x1 and x2 interact? In the relationship with y. These are all the same kind of question. And that question is asking, is this number b1, beta 1, 2, 0? Your lecturer probably just calls it beta 4. I like to give it a name that reminds me what it belongs to. So is beta 1, 2 equal to 0? And so you do a hypothesis test. Beta 1, 2 is 0. That's the vibe of linear regression. I might as well mention it now while I'm at it. Contrasts are trying to say some other question about the flavor of what the betas are. So you could be asking, for example, does beta 2, does x1, do x1 and x2 have the same relationship with y as each other? So maybe x1 and x2 are both weights, for example, of amount of food that you give things. And so maybe it might be that they have the same relationship, that every time you have an extra gram of this food, it has the exact same relationship with y as this having an extra gram of food. And so you would ask yourself, is beta 1 equal to beta 2? That sort of thing. So you could ask questions, do x1 and x2 have the same relationship with y? And that would be asking, is it true that beta 1 is equal to beta 2? And so your null hypothesis would be that beta 1 minus beta 2 is 0. Something like that is my understanding of, and so this is where contrasts come from. Yeah, that's my very, very basic understanding of what contrasts are trying to do. But I feel like there's some extra bits that I'm missing, but that's okay. I just wanted to get started. How are we feeling about all this? Regression is deeply connected to the story you're trying to tell. You have a research story that has data that goes with it. And so it's really important to be able to connect the story that's being told to the hypothesis that you're trying to answer and in particular, which parameter is involved. So there is a technical detail here that I need to talk about, is that the way that I've done this formula kind of assumes that the x's are numbers. Because I won't be able to do a calculation of beta 1 times x1 if the value of x1 is fish. Right? It doesn't make any sense. So this is, at the moment, the way I've talked about it is an assumption about the x's being numbers. And so we have to have a way of turning categorical variables into numbers to be able to ask questions like this. And so if you have categorical variable, this is my x1, what I was going to call x1, I'll just call it x, and x is A, B, C, for example. I don't know what they are. They could be colors. They could be home countries for people. They could be types of fertilizer for plants, whatever. Then you need a way of turning that information into variables. And so it's useful to think about what your individuals have. So the idea is that each person, if they're people, or they could be, you know, chicken chicks, or they could be petri dishes, or they could be whatever. Anyway, some of them have A, some of them have B. This one's also got A. This one's got C. This one's got B. They've all got their own letter for that thing, right? And you need a way of using numbers to tell you which category you're in, so that you can do it in the formula. And the way it's done is they're called dummy variables. Is that what the lecturer called them? Anyway, that's what they call them in economics, dummy variables. And so what you do is you try and use the smallest number of number variables to tell you which category you're in. And so what you can actually do is turn this into like a dichotomous key, like they would use in biology. And you would ask, is the person in category C? Yes, no. And is the person in category B? Yes, no. And then once you have the answer to both of those questions, you will know whether they are in A. And so that's all you need to know. And that will, and so if it's no, no, then that means they're in A, right? And so what you do is you create a variable that is xc, which is 1 if you're in and 0 if you're out. And this is xb, which is 1 if you're in B and 0 if you're out. And if you're out of both C and B, then you must be in A. That's how you create them. And so a categorical variable with 3 categories in the formula will produce 2 numerical variables. But they're numerical variables that can only be 0 or 1. That's how it's done. So the question of, is y affected by x, becomes, is y affected by xc and xb? That's what it becomes. Yeah. And so what you have is like yi is beta naught plus beta 1 x beta b xb plus beta c xc plus an error. That's how it would be done. So if you're in B, then this is 0, and you end up with, and that's 1. And so you end up with beta naught plus beta b as the value of yi, as the best prediction of what yi could be. And if you're in C, then that's 0 and that's 1, and you get beta naught plus beta c as the prediction of what yi could be. And if you're in A, then these are both 0 and you get beta naught as the prediction of what yi could be. And so what you end up with is like the mean in A ends up being beta naught plus beta B times 0 plus beta C times 0, which is beta naught. And mu B is beta naught plus beta B times 1 plus beta C times 0, which is beta naught plus beta B. And mu C is beta naught plus beta B times 0 plus beta C times 1, which is beta naught plus beta C. And so beta B becomes the difference between mu A and mu B. And so to ask the question of is being in category A different from being in category B is the question of asking, is beta B equal to 0? And to ask the question, is being in category A different from being in category C, is asking the question, is beta C 0? And is being in beta B different from being in beta C is asking the question, is being in category B different from being in category C? That's asking, is beta B equal to beta C? So is A different to B? That's asking, is beta B equal to 0? Is A different to C? Is asking beta C equal to 0? Is B different to C? Is asking, is beta B equal to beta C? And do any make a difference to Y? That's asking, are they all 0? At the same time. So this one is a contrast. There. Yeah. Okay. So when you do regression, this is a t-test. A question about a single variable is a t-test. This one's a contrast, and this is an ANOVA. You can do these ones with ANOVAs as well. But when you ask R to do a regression, it will give you a table with t statistics in them. And each t statistic goes with the question of whether that coefficient is 0 or not. But when you ask it to do an ANOVA, so if you do R, if you did R for this, so if you're in R and you had your data like this and you had like X and it came in flavors of A, B, B, C, C, A, whatever, and your Y was a number, that's what the data looks like, right? If you had your data looking like that, and then you asked R to do like LM Y twiddle X, for example, that's how you do it, right? Oh, and you tell it what the data was, yeah. Is that how you've been asking R to do these things? Yep. If you ask it to do that, then it would produce a table like this. It would say like intercept B and C like that. And it would have the coefficient and a standard error and a degrees of freedom and a test statistic and a p-value. Table would look something like that. Does that look familiar? And each of these p-values goes with whether that coefficient is 0. So these ants were beta something equals 0, those questions. But if you asked it to do and ANOVA on this. Now, this is how I'm not 100% sure how to get R to do the thing I want, but you can ask R to do an ANOVA. I think it's ANOVA, not AOV. Damn it. I can't remember the code. Can't remember the code, I'm sorry. You would have to look that up, some code to do an ANOVA. It might say, it'll just say like X, and it'll give you some SS's and an M and a degrees of freedom and an MS, and an F statistic and a P, something like that. Okay, so you get your R is this, and you do like ANOVA on R. Yeah. And it'll look something like that. And there'll be a total column as well, a total row as well. And this is answering the question beta 1 equals beta 2 equals 0. Yeah. So if your hypothesis concerns a single variable, it's from this T table. If your single parameter, it's from a T table. If your hypothesis concerns multiple parameters simultaneously, it has to go with an ANOVA. And it's actually, the ANOVA is answering questions of multiple parameters being 0 simultaneously. That's what that's about. If you want to, like, this will just make them all the parameters 0 at the same time, not the intercept. It doesn't care about the intercept. If you want to pick out specific parameters to be 0, then you have to do 2 regressions and to do an ANOVA that compares the 2 of them. I'm pretty sure if you do ANOVA and put 2 regressions one after the other, it will do a thing that compares them. Is that right? Yeah. So that's the general idea of what's going on. I'm hoping that's for some way helpful. I wanted to say one last thing before I said anything else. Since this is the first revision seminar in this course at all, which was that statisticians have this need to talk about all of this with linear algebra, like matrices and stuff. You don't need to talk about it with linear algebra. It does make it easier to teach a computer to do it. Because computers were designed after matrices were invented, based on the concept of matrices existing. And also Fisher, when he invented ANOVA in 1925, he thought about it as linear algebra, and the tradition has continued to this day. So just wanted to point out that when you see something like this, what this is describing, this thing here is a list of y1, y2, y2, 3, y4, all the way up to yn. And we're going to imagine that as a vector, like a column vector that has all of those things in it. And so this will have y1, y2, blah, 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 like that. And this will be like beta 0 plus beta 1 xi11 plus beta 2 x21 plus epsilon 1, like that. And so on. And then what will happen is that you'll, if you're concentrating, you'll notice that a string of pluses tends to come about in matrix calculations by doing a dot product. And a dot product is a matrix multiplication. So what they do is that they separate this out into this, like that. Put all these epsilon i's in their own separate, these are supposed to be 2's, David. Put all these epsilons in their own vector. And then you look at this and you think, aha, that would come about by doing by doing 1 x11 x21 times beta naught, beta 1, beta 2. This times this as a dot product would produce this answer. And then the next row would be made by doing this. And the next row would be made by doing this. Now, I just want to point out, I may have my indices backwards from what your lecturer does. They may do x31 in this spot and x32 in this spot. I'm sorry, I never remember which way around they're supposed to go, partly because of my mild dyslexia, and orderings of things is difficult for me, but I can do this. And what they do is they call this vector y bold or underlined on paper, this matrix X, this vector beta bold, and this vector epsilon bold. And so this contains all the information from my original formula for all of the individual data points. And then there's all these sweet linear algebra magic tricks that allow you to calculate the best value of beta from the data you've got. Because this here, this is the data, right? This is all of the values of X that go with all of your individuals. This is also part of the data too. And so your data in this story is here and here. And so you don't know what the betas are and you don't know what the epsilons are. And if you choose a particular set of betas, then these epsilons will behave a certain way. And if you choose a different set of betas, these epsilons will be different because your line or plane in this case of best fit will be in a different spot. And so your errors will be different. And you choose your betas in such a way that the errors do have a mean of 0. That's what you want. And if you do that, then it turns out that beta hat is, bear with me, I'm almost sure it is X transpose X inverse X, Y, like that? Yeah, okay. Which is, that is a calculus / linear algebra magic trick. Like, it is deeply cool. It'll only work if the columns of X are independent. So you can't use all the same value of x1 in this column, or that will be a multiple of this column. So you need to have at least 2 different x1s, at least 2 different x2s, and you can't use the same values for x2 as you do for x1 at the same time, or it won't work. Yeah, so anything else is fine. As long as the 3 vectors are independent, it'll be okay, because you won't be able to make this inverse unless Cole's independent. Anyway, that's just a magic trick, and I just wanted to point it out that it's there. And so when they talk about contrasts, they like to talk about them as linear algebra. And so when I have the question, is beta naught equal to beta 1 equal to beta 2, that's my hypothesis. Then I switch that into beta 1 minus beta 2 is 0. And beta 1 minus beta 2 is what I get when I put 0, 1, minus 1 times beta naught, beta 1, beta 2. And so this is a vector which they call lambda. Did they put a transpose on that? Or did they just call lambda? Okay, so, and like that, that's what they called it. And they went, okay, that's the thing. And so that's why contrasts are written that way, because they have this penchant for making linear algebra. And it should be possible to put this lambda in this formula somehow and make the computer do some matrix calculations that will turn out to be stuff. But I don't understand that bit yet. All right, I'm going to stop there. So I'm going to stop there and stop the recording.